Hey everyone, welcome to our first real physics lesson. The things we've been doing for the past couple weeks have all been preliminary. Tools we're going to use to help us study physics. Scientific notation, significant digits, measurement, graphing, all these things that are going to help us understand the world, but now we're really going to start putting concepts and ideas into all these measurements that we will be taking as far as the year goes on. Okay? This is your first real content video, and I really hope that if you're watching it right now, you encourage other people to watch it too. I'm really trying this experiment this year, but it really depends on you guys watching these videos outside of class. I'll try to keep them concise. There's only so much I can do though. Sometimes I gotta have to go almost like a class period. But I really think that you're gonna see that using the time on your own to where you're kind of just sitting and listening and doing that stuff on your own where you're passive, and then coming to class where we're a little more active and engaging the material, trying to figure some things out. I hope it's gonna work a lot better as far as understanding things, making sure that you have a good grasp of these concepts. Right? If you're watching, please make sure other people are watching. Like I said, I will make the slides available to you online so you can follow those slides along. Jot little things down if you want to. That'll be up to you, but I'll make those available to you. Okay? So for us, we're going to start our first real physics lesson, and for us in this class, the majority of the time we're going to spend studying mechanics, which is the study of motion. And we'll find out that when we study mechanics, that study of motion, we're going to be kind of encountering situations over and over again that we're going to look at in different ways. You'll see that we're going to do the same problem maybe 3 or 4 times as the year goes on, but just looking at it from a different aspect, looking at different things about that problem, making sure we analyze the whole situation, not just one piece there or one piece there. Okay? But we'll see that our study of mechanics, first I'm going to lay some ground rules for you, and then we'll see that it centers around 3 questions, and we'll introduce those questions today. And so it begins, everybody, our first real physics lesson. Today we're going to intro mechanics, the study of motion, as I mentioned previously in that little intro video, and we're going to introduce 2 really big concepts that go along with our study of mechanics, and we'll talk about those in just a second. But first, though, want to make sure that you understand where we're starting from, because what we're going to do in this first section is not the complete study of mechanics. All right? We're going to start simple. We're going to start building foundations, introductory basic concepts, because we're going to use those concepts the entire year. So let's start a couple of ground rules to start off, okay? At first, we're only going to describe the motion of an object, and we're not going to explain what its cause of motion is. That comes in a later chapter, 2 chapters from now. Right now, an object is moving. It may be speeding up, it may be slowing down, it may be going at the same rate, but it's already moving. We're not going to talk about why it started moving, or why it's currently moving, or why it's speeding up, or why it's slowing down, only that it is moving. Next, the motion that we're going to study will only occur along a straight line, one-dimensional motion. If you think about, from math class, a coordinate plane, x-axis, y-axis, is 2 dimensions, the x dimension and the y dimension. Right now, we're only going to start in 1 dimension. It's a lot easier to handle mathematically. So we're going to start there. Eventually, we'll get to 2 dimensions. We're not going to do 3 dimensions in this class. It just gets a little hairy mathematically, but if you understand the concepts, especially when we jump from 1 dimension to 2 dimensions, you should be able to handle 3 dimensions with a little bit more patience, but that comes at a little later time. Right now, 1 dimension only. We're moving in a straight line. And last, we're going to consider all of the objects, or these moving objects that we're going to talk about in this first part here, as solid objects, simplified as a point. So if we're talking about a bicycle coming down the road, we're not going to talk about the fact that, the pedals are turning at one rate and the wheels turning at another rate, and the guy has a head that he twists and turns to look around, stuff like that. We're not going to get into that. Our bike is just our object, one object. We're not going to consider it as a complex object with moving parts. Eventually, we'll get into some of that when we have different parts of the same object moving in different ways and how that affects the motion, but right now, not what we're going to do. It's just too complex, so we're not going to handle that right now. Okay? But regardless of how we study motion or what ground rules we set, When we study mechanics, there are always three questions that we are looking to answer. And they're three simple questions. And you'll see and you'll hear me as the year goes on ask you these three questions over and over and over again. Because that's what we do when we study mechanics. We look at motion and we look at it from different ways, different aspects, different angles, different viewpoints. But we're always looking to find out the same three things. So the first thing we want to know is, where is that object? We got to know where something is if we're going to describe it to other people. The second thing we want to know is, what is that object doing now? What is it currently doing in its current location? And then the third thing that we want to know is, what will it be doing in the future? Is it changing somehow? And if it is changing, how is it changing? Because that's going to help us predict what's going to happen in the near future. But in a logical fashion, we need to start with question number one. Where is that object? Okay. So our study of mechanics begins where all good discussion should, with Batman. He is the Dark Knight after all. So the first question that we said we wanted answered when we were talking about describing the motion of the object was, where is this object? So I'm showing you Batman, but right now it's kind of hard to describe where Batman is. He's standing on, something black, and it appears that there's some kind of a light behind him, or a reflection from a light behind him. But that doesn't really lead us to any kind of probable conclusion about where Batman is. If I'm just showing you this picture, you might be able to guess where he is, but just from this picture, you really wouldn't know for sure. So what I'm going to do is I'm going to pan out for a little bit, maybe twist a little bit, and we'll see that, of course, Batman is just to the left of Einstein. Where else would he be? I mean, Batman and Einstein are pretty good friends. But once again, you have this Einstein action figure. All right, let's not call him a doll, please. He's an action figure. And you know that Batman's to the left of him, but that's not really helping us too much, because where's that Einstein action figure? Who knows? So we pan out a little bit more, and we see that Batman and Einstein can be found just behind this red dune buggy. Because, they got to have mode of transport, right? Red dune buggy is good as any mode of transport, I guess. So now they're right behind that. But once again, we run into that problem of, well, where's the red dune buggy? Okay? So I'm going to pan out a little bit more, and we start seeing some other things come into the picture. Oh, look. There's a chemistry gas jet, right? So now Batman, located just to the left of Einstein, just behind that dune buggy, and just to the left of, or I guess depending on which way you're looking at it, to the right of that gas jet, okay? If you're looking at the screen. Okay? But how many chemistry gas jets are there in the world? A lot, true. So could we really find Batman from this information? Probably not. So we pan out a little bit more, and we start seeing, oh wait, there's another gas jet. So we know wherever Batman is located, there's two gas jets. But once again, not really helping us a whole lot. Pan out a little bit more, and we start seeing, oh, desks, cabinets, things of that nature. Okay? These are the kind of things that we can start using as reference points to locate where Batman actually is. So now we know he's in a classroom, most likely. Okay? We can give some directions based on some markers in that classroom, but how many classrooms are there in the world? Chemistry classrooms, chemistry science-y classrooms, right? There's a lot of them. So then we pan out a little bit more, right? Trying to keep Batman still in that picture. And now we have some more things in that classroom, right? A teacher's desk, an inconveniently placed eye wash and shower station, a sink in the background there. You guys probably know where this is heading. You know where Batman is now because you have a certain experience. You have a certain frame of reference in which to locate Batman. And that's where we're going to spend the next part of this discussion talking about the importance of what we refer to as a coordinate system or a frame of reference. Okay, the whole Batman saga that you just witnessed is a good introduction to this question of where is the object. It's not as easy of a question to answer as it may seem originally. One of the things that I tried to reinforce with you from the panning out and the including more landmarks around where Batman originally was the importance of this idea that we call a frame of reference or a coordinate system. As far as the definition, we refer to it as the context in which we study motion. In regular person terms, we describe it as where are we making all these measurements from? If we want to tell somebody where something is, and we want to get them to that point, or really truly describe where it is in order to get that person a better picture of what's going on, we need to give them some landmarks. Like, okay, if you want to get, if you want to get to my house, I got to give you some place to start, okay? Then give you directions based on that, okay? A good frame of reference will include two things, a reference point and a directional system. So, taking the example that I just gave you, if I want to say, hey, come to my house, okay, I need to know first where you're starting from, and then give you directions based on that starting point. Okay? So that starting point is going to be your reference point. Okay, where am I making all these measurements from? And then directional system, that's something that we kind of have built in a map or like direction or like when we're driving or something like that, using like north, south, east, and west. Sure, we might be able to just use left and right, but depending on where you're starting and which way people are going, that might change. These are the things that we have to take into consideration when we're talking about describing the motion of an object, and at this point, specifically the where part. You guys all had a chance on Wednesday to work with the motion detector, and the motion detector is a really good example of a frame of reference. The motion detector has a built-in frame of reference that it uses all the time. It has a reference point. It calls itself the 0 point. So it says, okay, if something is right next to me or touching me or in contact with the front of the motion detector, I'm going to say that it's 0 meters away. Right? But then the directional system is something that you're familiar with from your analysis, from your experiment on Wednesday during block day, even though you may not think so. The motion detector calls everything in front of it a positive value, and it calls everything behind it a negative value. Now, that may not seem like north and south, but that's enough to distinguish one way from the other. And the motion detector only works in one dimension. So in this case, it really only has to distinguish two ways, a frontwards way and a backwards way. And it does that by using positive and negative, just like a number line in math class. We distinguish one way on the number line as positive, the other way on the number line as negative. Okay? Then you look at if you look at your graphs from the other day, and I'll draw some stuff here on screen, hopefully it's going to show up. Okay? Very slow, not good at all. Okay? But if you look at some of your pictures from before, okay, let's see if I change this. Great, now my line shows up. Awesome. All right, let's get out of here and see if this works. Sorry, everybody, I'm kind of doing this on the fly. I know it's not like the best production value in the world, but hopefully it'll work. Standing by. If you take a look at some of your graphs from the other day, the LabQuest was giving you an XY axis, and on the x-axis was always time, and on the y-axis was position. And if you take a look at, say, like when you shot the car up the ramp at the motion detector, it gave you a graph that kind of started like this, nice little parabola, looked like that, and then it ended up something like that. Or it might have bounced if you didn't catch it or whatever, okay? But if you take a look at these values, right, the y values of these dots that represent or that are on the parabola, the y values are all positive. They keep getting smaller and smaller and smaller positive, but they're still positive. If we go back to this picture and check this out, hold on one second. Okay. Let's copy this and let's paste it in here. Right? Ooh, very big, but in this case here, right, I know the arrow on the cart is going the other way, okay? But if this cart was moving in this direction, okay, it's still on the positive side of the reference point. It's getting closer and closer and closer, which the motion detector shows by values in the positive direction getting smaller and smaller and smaller, but it's still on the positive side. And then when it starts moving away from the motion detector after it gets to the top of the hill and stops and slows back or goes back down the hill, right? These positive values keep getting bigger and bigger and bigger in number because we're still on the positive side of 0, just distinguishing one side of the motion detector from the other, but we're getting farther and farther away. That really illustrates the importance of the frame of reference in the directional system. Now, within that frame of reference and directional system, we want to answer that question, where is the object? There are two terms that we use to somewhat describe where an object is. And those two terms are position and distance. Distance tells us the separation between two objects. So we can talk about how far away Batman was from Einstein. We would say that Batman is a certain number of meters away from Einstein. But does that really tell you where Batman is? And it doesn't, because we need the second one, the one on the top that says position, the separation between the object and some reference point. If we talk about the distance from Batman, or between Batman and the door of room 246 at Westlake High School, and I tell you that Batman is, I don't know, let's say 5.5 meters in the south, or let's say east-southeast direction from the door of room 246 in Westlake High School, could you find Batman? Yeah, you're going to have a lot better chance of finding Batman than saying Batman is 5 centimeters away from Einstein. Okay? A little bit more detailed. Position is a more detailed description of where the object is than distance, which just tells you the separation between two objects. So when things start moving, this question of where is the object can get a little bit more complicated. When Batman's just sitting there on the table, as long as we have a reference point and a directional system, we can describe his position, his location relative to whatever reference point we choose. But when things start moving, we have to take into account a couple of things. Mainly, we need to take into account where it starts, what it does in the meantime, and then where it finishes. So right now, you're seeing a picture of our red buggy that Einstein and Batman were hanging out by before, sitting on the lab table, a meter stick next to it. We're going to use that meter stick as a directional system. Now, or as a frame of reference. Now, usually, it's kind of easy if we zoom in here on the meter stick. See if this actually works. All right. Ooh, too bright. Let's see if we can get rid of that. Maybe we just need a little focus here. There we go. So, meter stick generally starts at 0. So it probably makes sense to call the beginning of the meter stick our reference point. That's going to be our 0 position. If we say that something is located at 0 meters, we're saying it's located right here. Okay? And then, just like regular meter stick, okay, it's probably getting a little too bright for you to see, but if I zoom in, you can see that it just goes up, positive, 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 40, 50, etc., etc., etc. Okay? So, here's the beginning of the buggy, and if I zoom in, this buggy starts at around, oh, sorry, brightness issues. This buggy starts at around 24 centimeters. So I'm going to back it up, see if I can do this with one hand. Might be a little difficult, but we'll give it a try. So I'm going to start this dune buggy, and it's going to go to somewhere around there. And I'm going to stretch it out, and I don't have a long enough cord, so I'm going to do some movie magic here. This is pretty good magic, isn't it? And we end up somewhere in the low 80s. Right? Then what I'm going to do is I'm going to turn it around. Okay? So now, same red buggy, facing a different way. I'm going to turn it on again, starting somewhere, let's see here, somewhere in, somewhere in the high 70s, somewhere around there. Okay? I'm going to back it up. I'm getting all choppy. That's not making me happy. Alright. Then I'm going to start up my buggy again. I'm going to run it down this way and stop it somewhere closer to the 0 point than it ended up before. So like we stated before, when we're studying mechanics, our study of motion, there are 3 questions that we want answered. And that first question that we've been talking about is that where is the object question. When we started off with the Batman demonstration, Batman was stationary. As long as we had a reference point, as long as we had a directional system, we could identify and give directions as far as where Batman was. But when things start moving, it gets a little more complex. And as I mentioned during the red buggy demonstration, there's basically 3 things we want to know. Where the object starts, what it does in the meantime, and then where it ends up. And sometimes those things are more important than others. There's basically 2 terms that we use in order to describe the motion of the object, or answer the question of where is the object while it's in motion. And those 2 terms probably sound a little similar to you, but they do have some differences. So the first term is distance traveled. The total distance required to get from one position to another. If we go back to that red buggy demonstration, the object starts, and I'll give you some numbers in just a second here. The object started at around 24 centimeters away from the reference point. We might call that positive 24, going back to our directional system and frame of reference that like the motion detector sets up, which we mentioned a little earlier. So that object started at positive 24 centimeters away from the reference point. And it moved to positive 83 or 84 centimeters. I forget the exact number, but whatever. Okay? So that means that that object moved approximately 60 centimeters. That's the distance traveled, required to get from one position to another. And then for the second demonstration, when it came back the other way, it started at, I don't know, it was like 78 centimeters, positive 78 centimeters away from the reference point. But then it ends up somewhere around, I don't know, 12, positive 12, or something along those lines. So if you go from 78 centimeters to 12 centimeters, that's about like 66 centimeters. So those are distance traveled. However, when you're describing the motion to somebody, those 2 red buggy trips are definitely different. One went one way and one went the other way, other than the fact that they were obviously different lengths. So there were different distances traveled there. However, another term that we're going to use more often to describe the motion of the object is displacement. We refer to displacement as the change in position relative to a reference point. So hopefully you remember from math class, or maybe a previous science class, that when we talk about the change in something, we use the Greek letter delta. And it looks like a triangle, but it's a Greek letter. It's actually a capital delta. Greek letters come in capitals and lower cases, and we'll see some of them a little bit later on. But whenever we talk about the change, we're talking about delta. In order to know the change in something, we got to know 2 things. We have to know where that object starts and where that object finishes, if we're talking specifically about the change in position. So where does it start relative to the reference point? Where does it end relative to the reference point? And whenever we talk about delta something, regardless of what that delta is, the change in something, we generally calculate it as final minus initial, right? Where did we end up minus where we started, and that's going to give us what the change in that quantity was. And that holds true as well when we're talking about displacement. Remember our definition of displacement, the change in position relative to a reference point. So if we're going to use, or if we're going to follow that logic of what delta is, if we're calculating delta x, that's the term, or that's the symbol that we use to represent displacement. Y remember we talked about that in one dimension, which is how we're going to start our discussion of mechanics, our frame of reference, or the context in which we study motion, basically looks like a number line. You have a 0 point, you have a positive side of the number line, you have a negative side of the number line. Because of that, a lot of times books will use x, sort of representing the x-axis that this object is moving along. So if we look at the change in position, delta x equal to x final, where it finished, minus x initial. Your book uses delta d, but the concept remains the same. What unit are we going to use to measure displacement in? Position is a distance, right? How far away from a reference point are we? So if we're taking a position, which is measured in meters, minus a position, which is also measured in meters, unit analysis from the first chapter, meters minus meters, that still gets us meters on our number. So we measure displacement in meters. Here's a quick example summarizing what the red buggy demonstration was sort of all about. My red buggy in this case has been replaced by a gecko. Fine, whatever. Didn't have a picture of a red buggy. So anyway, the first demonstration, hopefully you remember, the red buggy started somewhere around 24 centimeters, all right? And then I moved it, in this case, in the right, towards the right, all right? But more importantly, in the positive direction relative to our reference point, to somewhere around 85, 84, something like that. If we back it all the way up, remember, when we're talking about position, when we're talking about where is the object, we have to do it within the context of a frame of reference. Where are we making all these measurements from? And hopefully this doesn't annoy you, but I'm going to take this, I'm going to take this picture, all right, take it out of here, and put it into my notebook software. Open it up. So, going back to all these things that we talked about. Sorry. I'm going to reduce my size a little bit so I have some room to draw. This 0 point on the ruler, that's going to be my reference point. That's where I'm going to make all of my measurements from. And like we just discussed, generally the frame of reference has, not generally, the frame of reference is going to have a reference point and a directional system. Because we're dealing with one dimension, a straight line, we basically can distinguish one way from the other way, real simple using math concepts that we've learned. If you only have two choices, you can call one of them positive, you can call one of them negative, and you'll end up being able to distinguish this side from that side. Based on the numbers on our based on the numbers on our meter stick that we're using, we're going to call the direction towards the right on your screen the positive direction. And then we're going to call the direction towards the left on your screen the negative direction. So this gecko starts, his initial position is 24 centimeters, except if you look at the reference point and we say that that gecko is 24 centimeters away from the reference point, there's two options. He could be on the positive side of the reference point, or he could be on the negative side of the reference point. His distance from the reference point is 24 centimeters. But if we want to know his position, we also have to include what side of the reference point is he on. And we can do that just by distinguishing positive and negative. So this gecko's initial position is positive 24 centimeters because he's on the positive side of 0, the reference point, and he's 24 centimeters away. Then that gecko moves down here to somewhere around 84, maybe 85, okay? But once again, his final position, if we're talking about position, we not only have to talk about how far he is away from the reference point, but we also have to talk about what side of the reference point is he on. So once again, that's going to be positive 85 centimeters. If we go back the way that we defined displacement, the change in position before, right? Something to keep in mind. The green numbers are all in relation to the reference point. They are positions. Remember, our definition of position is location relative to a reference point. But when we're talking about displacement, we're talking about a movement.
where are we now in relation to where we originally started? So we said to find anytime we have a delta or a change in something, we're going to go the final value minus the initial value. So this gecko ended up at positive 85 centimeters. That's his final position. We subtract the initial position, which is positive 24 centimeters. I think we're at the point now where we can do this math, and we end up with 61 centimeters. Good there? Hope so. All right, I'm going to do a little magic here. Go back to my PowerPoint, but I'm going to take the gecko's second trip. So I'm going to go and grab this picture here. Pay no attention to the bottom of the screen. Okay, for the second trip of the red buggy, which was along the same line but back in the other direction, we have to distinguish that somehow, some way. If we talk about the distance that something travels, it really doesn't matter which way we're going, right? We talk about how far we've gone, the total length of the trip between starting point and finishing point. However, most of the time, when we want to accurately describe the motion of the object, we have to take direction into consideration. So, if we take a look at this second trip of this gecko here, okay, his initial position, he starts at, let's say, 78 centimeters. But once again, if it's a position, we have to go in reference, we have to state his position relative to the reference point. This frame of reference doesn't change. This is still our 0 point. Okay? Then we still have a positive direction, which the gecko is still on that positive side of 0. So now his initial position for this trip isn't 78 centimeters. He's 78 centimeters away from the reference point, but his position will be positive 78 centimeters, indicating which side of the reference point is this gecko 78 centimeters. Final position in this case, still on the positive side of the reference point, but now we're somewhere, I don't know, let's say 13 centimeters. Okay? So we're 13 centimeters away from the reference point on the positive side, so that's plus 13 centimeters. Displacement we just talked about was the change in position. The final position minus the initial position. The final position in this case is positive 13 centimeters. Minus the initial position in this case, which is positive 78 centimeters. You do a little math, and hopefully, if you do your math correctly, you end up with a negative number, negative 65 centimeters. Is that a problem? No, that's not a problem. That's how we distinguish the one direction from the other direction. The positive and negative, we said, is part of our frame of reference, part of our coordinate system, and it distinguishes one way from the other. So if we say that this red buggy or gecko or whatever it is had a positive displacement, like here, right, that indicates movement in a certain direction, the positive direction in whatever we set up our frame of reference. If we say the gecko has a negative displacement, that just says that that gecko is moving in a negative direction, or the opposite direction, or whichever way we establish negative in our frame of reference. That leads us to our discussion of vector quantities. Vector quantities are going to pop up all year long. Okay? Vector quantities, like it says on the screen, indicate both magnitude and direction. Vector quantities will answer two questions for us. They will tell us how much and which way. That's important, especially if we're talking about describing the motion of an object or some various other things that we'll come across later in the year. We want to know not only how big they are, but also which way they go. All vector quantities have to be defined in relation to some reference point within our frame of reference, within our coordinate system that we choose for whatever problem that is. Vector quantities in one dimension I've made mention of this already, can be distinguished as positive or negative, because in one dimension you only have two choices. You either go one way or you go the other way. Now when we get into two dimensions, that's going to change, but we won't worry about that right now. In one dimension, vector quantity can be positive, it can be negative. On the other hand, there are things out there that don't have direction associated with them, and eventually it will show up. And those are called scalar quantities. Scalar quantities only indicate magnitude, which means they only answer one question for us, and that's how much or how big. Okay? Distance traveled is a scalar quantity. If I talk about how far that buggy went in the original demonstration, I could say, or the gecko from the two pictures, I could say in the first case the gecko went 61 centimeters, and in the second case the gecko went 65 centimeters. And that would be fine to describe the distance. But if we're going to really talk about describing the motion of the gecko or the motion of the buggy, you have to talk about, okay, I went 61 centimeters, but which way did I go 61 centimeters? Because if you're describing the motion or trying to analyze or measure the motion of that object, direction is important, because 61 centimeters in one direction is different than 61 centimeters in the other direction. Other scalar quantities include things like mass, temperature, time. Those don't have direction to them, ones that are shown up on the screen there, right? But we can still measure that stuff just without a direction component to it. Now that we've introduced the first concept that we're going to talk about in terms of our first physics lesson, remember we said there were 3 questions, and we basically answered the first question. And the first question was, where is the object? And we learned that the answer to that question is actually position, right? Where is that object relative to a reference point? And then we talked about what happens if the object moves and changes positions and things like that. What we're going to do next is we're going to talk about the second question. What is the object doing now? And we'll talk about the answer to that question in just a second. The third question, what will that object be doing in the future? That's a little bit down the road. Okay, that's for another time. So, but anyway, let's talk about the answer to that second question. What is the object doing now? The answer to that second question is called velocity, or average velocity, and we use the letter V. Sometimes you'll see the AVG subscript on it, but definition-wise, the velocity is equal to the displacement divided by the time interval during which that displacement occurred. So V average is equal to delta x over delta t, the change in position over the change in time. Units on velocity have to come from 2 units, right? This is going to be a derived unit because we can't measure distance and time in the same unit. It's actually 2 measurements, right? It's a ratio between distance and time, but we got to measure distance, we got to measure time. So our units are going to be meters per second or meters over seconds. So let's take a look at this picture here, and I'm going to get out of PowerPoint and go to my notebook software. All right, so here, let's go here. So what is the average velocity of the runner in the figure? We just learned that our definition of velocity was equal to, the average is equal to delta x over delta t. So we need to know the displacement of this runner and the time over which that displacement occurred. We just learned in the previous part that displacement was equal to x final minus x initial, right? The change in position. Where do we end up versus where did we start? So if you look at the picture of this runner here, it shows you the runner running the whole 100 meters, but as far as time frame is concerned, pretty much looks like that runner stops right about there. So if we look at x final, that runner is going to end up at 50 meters. But remember, because it's position and it's a vector quantity, we have to make sure that we go direction-wise. Here is our reference point. We labeled it 0, and it looks like that we've called this the positive direction and this the negative direction, seeing as how all the numbers here on this number line, they don't have negative numbers, they don't have negative signs in front of them, so we'll just call that the positive side. Final position, positive 50 meters, minus the initial position, which was the reference point, so we'll go 0 meters there. We do a little math, we end up with the displacement of positive 50 meters. Then if you look at the stopwatches that are concerned here, right, delta t, same thing, right, t final minus t initial. And if we look, final time looks like it was 6 seconds minus the initial time, which was 0 seconds. So we end up with a time of 6 seconds, or a delta t of 6 seconds. You better make sure you have positive delta t's, because if you have negative change in time, we have an issue. Okay? So we take those values, plug them back into this equation for average velocity, displacement of positive 50 meters over a time of positive 6 seconds, run that through your calculator, and you should end up with positive 8.3 meters per second. And that's going to be the average velocity of the runner during that time. Let's go back here. Something to keep in mind that we just came up with. When you do that math problem, you should end up with a positive 8.3. Velocity is a vector quantity. It has a magnitude and it has a direction. So it answers those two questions, the how much and the which way. In order for us to define vector quantities, we have to first set up our frame of reference, or our coordinate system, just like we talked about with the motion detector. And we talked about that in the previous example with setting up the starting line as the reference point, calling one direction positive, one direction negative. Remember, in one dimension, all we need is two things to distinguish one way for the other, because that's really the only choices that we have. Velocity can be positive or negative depending on the direction of the movement, not necessarily where the object is located. When you're talking about position, it's where it is relative to the reference point. So if you have a positive position, that means we're on one side of the reference point. If you have a negative position, you're on the other side of the reference point. But velocity doesn't work that way. Velocity depends on which direction you're moving, not necessarily where you are. As an example to illustrate that, we have these two geckos. The same two geckos from before. But what I'm going to do for you is I'm going to calculate some average velocities for you. And you should do these too. If you want to press pause and then do these on your own, do them real quick, and we can compare answers. So I'm going to do these silently here in a second and show you the two average velocities to compare what we were just talking about with the positive and negative velocity. So when you run that through, you should end up with positive 15.25 centimeters per second. Sig digs aren't right, but at this point, let's not worry about that. Okay? Here's the second gecko picture. Do exactly the same thing that I just did. If you want to, press pause, do it on your own, and then you can watch me do it. All right, when you run through those numbers, you should get negative 22 centimeters per second. That's what the math is telling us. But remember that the negative sign tells us something. Velocity is a vector quantity. It has magnitude, it has direction. the negative sign is telling us that that object is moving in one direction versus the other direction, which would be the positive velocity from the previous example. From the pictures, you can see, hold on, from the pictures, you can see that these two geckos are moving in different directions. One's going to the right, one's going to the left. In one dimension, we distinguish that with the positive sign on one, the negative sign on the other. Something to keep in mind, the negative doesn't necessarily mean slow. So get that out of your head as far as math class is concerned. Negative numbers aren't small numbers. Negative numbers are telling us a certain direction. So actually, in the second example, the one where the gecko is moving to the left, where we calculated that velocity to be negative 22 centimeters per second, whereas in this one it was only positive 15.25 centimeters per second, okay? The gecko is actually moving faster in the bottom picture, even though the velocity came out as negative, because the negative sign isn't telling us small, it's telling us a direction. Speed. Velocity has a scalar equivalent, and we call it speed. Speed is the scalar equivalent of velocity. Remember that a scalar value only has magnitude, no direction. So a lot of times we refer to as speed as the magnitude of velocity. Why? Because it's only telling us how fast. It won't tell us which way. Okay? Speed is defined as distance traveled divided by time. So whereas with velocity you're worried about displacement, which is where you start versus where you finish, with speed you're talking about distance traveled, which is the whole trip, the length of the whole trip, divided by the time it takes you to get there. Okay? Speed doesn't depend on direction. There is no positive or negative speed. It's always positive, because it's only telling you how fast. Last topic, instantaneous velocity. Hopefully you know, because you take English and you know English, when we talk about something being instantaneous, we're talking about like in the moment, right now. And that's what instantaneous velocity tells us. Average velocity tells us displacement over time, how long it takes you to cover a certain displacement. But if you don't travel in a straight line, which we haven't encountered a situation like that before just yet because we're dealing with one dimension, average velocity can also be how you'd have to travel, how fast you would have to travel in a straight line to get from where you started to where you finished. But for more practical purposes, instantaneous velocity, as delta t gets smaller, as the time frame over which we're looking at the displacement gets smaller and smaller and smaller, there is a smaller chance that we change velocity within that time frame. And when you get delta t smaller, 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 okay, the average velocity calculated over that very small time frame becomes what we refer to as the instantaneous velocity, or how fast we were going at a particular moment in time. So we'll talk about, you'll hear talk about that as we go along, and problems want to know about instantaneous velocity, and when we do labs in the lab quest, we'll talk about instantaneous velocity. That's the velocity right now. What is this object doing right now? And that's our last topic as far as velocity is concerned.